Okay, so what I have for you today, it's going to be quick today because this is one thing and one thing only that I really want to get my point across today, which is there, the Gauss's law. This is, I would call this the highlight of the course. But the good thing is because today is like a sort of like a holiday. So, all right, just sort of like, get some physics into your head and then we just, like, do something else in the afternoon. Okay. So, before we get to that, let's do one more exercise to summarize what we did last time about flux calculation, shall we? All right, because I have one more piece of maybe you can call it like a tip, or maybe is you can think of it like the intuitive way of understanding the flux calculation or the dot product that we built last time, if you remember this example over here. So the way that we calculated flux, we already said that, hey, Ajahn, it's just looking at the dot product between the electric field vector, that's the E, and then you take the dot product with the A that we already now built this as a vector now. Okay. And the way that we built this vector is whenever you see an area, the area vector is going to point perpendicular to that piece of area. All right. And that we use that as the direction for that area. And that will be the direction for the area vector. Okay. And of course, the magnitude of the area is just the width times the length of that area itself. So once the area has a direction, now the only thing that you need is just take the electric field E, dot with the A, and now we knew that every time you do the dot product, it just means that you only want the two vectors that are pointing in the same direction to do the multiplication or to do the product between just only the parallel components. All right. But because the way that we define the area vector is perpendicular to the real or the actual piece of area, so that means if E is parallel to the A, it's a guarantee that E is pointing perpendicular to the area. That's what we want for the flux calculation. Cool? All right, so that's what we did last time about flux. So what we want to count. We want to find the quantitative numbers for the flux. And the way that we do that is we count, even though we not really count, but that's what it is. That's not I want to clap there. I mean, we just want to get the numerical value for the number of electric field lines. So what we want is we just only take into account the electric field that piercing through the area in the perpendicular direction. I don't know, I just do my hands here. All right, so that's what we want. We want the perpendicular direction of the E through any piece of area. That's what the flux calculation was all about. And we do it very compactly by doing just the dot product between E and A. Cool. All right. So we saw this particular problem last time. So this is probably the hardest one from the last lecture, how we calculate flux in like a oriented piece of area, the slanted surface of this triangular box here. All right. So that was fine. So now let's do something, even though it looks kind of like nice and neat, but actually, if you look deep into this problem, it's more complicated. The question is this: a cone with base radius r and height h is located on a horizontal table. You have a uniform horizontal electric field penetrated from left to right as shown. So they want you to determine the electric flux that enter the left side of the cone. They don't want the whole electric flux for the whole thing. Why? I think because now look at this one. And if I ask you, hey guys, what is the net electric flux? You would say that is zero again. Why? Because electric field line piercing into this cone on the left side of the cone, and all of those field lines eventually going to exit on the right. So that's pretty much, there's no net. It's in equal to out. So you guys know there's no flux in the bottom. The bottom flux is also zero because there's no penetration of these electric field lines through the bottom surface. So everyone already learned this one a couple of times, that the electric flux is going to give you zero value. However, this particular problem asking you to figure out just the one, those lines that get into the cone. That's mean the left-hand side of the surface. How much is that? Okay. So when you think about it, Ajahn, we already learned this one. The way that you do it, you cut this surface into a tiny piece, and because we know that the area vector is going to point perpendicular to it, I can call this like a dA. And then you just figure out the angle between E and dA, and then you do the E dots dA, right? E dA cosine theta. However, the difficulty of this problem is this. If you imagine that you have to figure out the direction of the dA across this cone, see, the area vector is going to point like that. It's crazy direction, right? You can imagine that, right? Because the area vector has to point perpendicular to the surface. And then you look on the side, well, John, that's not an easy task to figure out the angle between E and that dA vector across the surface on the side. How are we going to figure this out? All right, that's the thing. All right, and this is the explanation I really want to show you. Go back one problem. Look at this one. If you still remember when we were doing the slanted surface, okay, let me highlight this one in black. Okay, and then when you look sideways, okay, but Ajahn, that is fine. Electric field is going in the horizontal direction. The area vector of the slanted surface is going to point perpendicular to it. That is fine. We figure out the angle. But the way that we did last time, where we showed in the calculation that it turns out the dot product that you were trying to calculate eventually lead you back to the area of the vertical piece of this slanted surface only. Remember that one? So when we were trying to do the calculation, we want the area of this slanted surface. So that's no big deal. But then when you want just to do the dot product between the slanted surface area vector and the E, you have to do that cosine 60. And then when you do the cosine 60, you only care about this tiny component here, right? This is the component of the A that points in the same direction as E. And you guys sort of now familiar with the concepts of the area vector. If the area vector point in one direction, so it must be representing the real area that is perpendicular to it all the time. So that means that tiny piece of area over here must be representing the actual area that is perpendicular to this. You guys with me? Does that make sense? And if I pretty much like slide this one on the left, so there's no doubt is this piece of area over here. So this is the reason why when you take only the component of the slanted surface vector that is pointing in the same direction as E, at the end, you only have to take care of the area that I'm highlighting black right now. Super black, dark, super dark area over here. That is the piece of area that you took into your calculation. But now, this is the way that I can imagine this piece of area came from what? All right, even though you saw it, it came from geometry to trigonometry. You do the cosine, theta, on and on. But another way to look at this one is this. If I shine a light, if I have a flashlight, and I put a beam of light in the direction of the electric field. Okay, let me say that. All right, so I put the beam of light parallel to the E. It could be anti-parallel, parallel doesn't matter, but at least it must be in the same direction as the electric field. And you shine the light on this one, that slanted surface, okay, that inclined area over there will cast a shadow on a screen that is perpendicular to this. Okay, let me sort of put a perspective. It's not supposed to be a perspective though, but anyway, the point is, if I have a screen behind this and I put a light, okay, flashlight, shine the light onto that slanted surface, it's going to cast a shadow. And the shadow is exactly that blackened area that I just drew over here, right? So now you can imagine that it turns out every time that you do the dot products, it's just like you only care about the area that is perpendicular to the electric field line, right? That's the definition of the flux pretty much. So that's why we can imagine by, hey, if I shine a light in the direction of the electric field onto the surface, and the only area that we care to take into our calculation is just the area of the shadow that being casted on a screen that is perpendicular to the beam of light, which is in the same direction as E. Are you confused a little bit here? If you're still confused, okay, go back to our present example over here. So think about this one. You start to think like, Ajahn, I don't think I can do the cosine theta because the cosine theta, I don't know how to figure out the theta for all the pieces on that left-hand side surface. But if you now shine the light in the direction of E, okay, onto this cone, and then I have a screen waiting. Okay, I have to draw a little bit cleaner here. There you go. I have a screen waiting on the back. What the cone will give the shadow, what is the shape of the shadow that the cone will give on the screen? Ajan, you say, okay, Ajan, it will cast the shadow in the shape of a triangle. Does that make sense? This piece of area right here, same thing. There you go. Cool. This is the area that you really need. This is a perpendicular that we have been talking about it since the beginning of the definition of flux. Because this is the component of those left-hand side surface of the cone that is perpendicular to E. The other components we throw away, we don't care. We only care about the components of the area that is perpendicular to the electric field. So that's why I sort of like give you the beam of light that's shining in the same direction as the E. And let's take a look at the shadow casted by the surface. I only care about the area of the shadow. And I'm going to take that area to multiply by the E because that is a guarantee. The E is going to fall perpendicular to this shadow. Cool?
Okay.
Okay, so that's why what we care about is only figure out the area of the shadow, which is quite easy to do because now, okay, but John, this is the base is going to be 2R. The height over here is going to be H. That's those information are given already. So that piece of area that is on this screen over here is going to be 1/2 times the base times the height. So that means the flux on the left side is going to be just the E times the A perpendicular. That's it. Okay, I can cancel 2 out as well. So there you go. Bam, bam. And that's it. It's E or H. But wait. Because when you look at the shadow, now the shadow is no more a closed surface. It's like a free floating piece of area right here, right? Because it's just a free floating area, right? So when you talk about the direction, you still have 2 directions to talk about. It's either point to the left or it can be either point to the right. But because right now, what we have over here is, of course, look at this one. Everything is point leftward. It's toward your left-hand side. So that means you only take the component that is eventually is going to point left. Does that make sense? So that means it's equivalent to you care about the one that point to your left. That is your A. Let me call it like a left vector. Cool? So that means it's make 180-degree angle with the E. So that means you need to take the cosine 180 along with this as well. Does that make sense? All right. And that means you get negative sign, which has to be because on the left-hand side of the cone, electric field is entering the cone. So when it's entering, it's a negative flux. So if this problem were to ask you, what is the electric flux on the right-hand side of the cone? It's going to be, you just look at the same area of the shadow. However, you're going to take the rightward vector direction to be representing the right-hand side surface of the cone. So on that surface, on the right-hand side, you have a positive flux, but same value, E or H anyway. So that's why if you take the sum of the two, you're going to get net zero flux. But because this problem only care about the left hand side. So it's a negative ERH and you are done.
Okay.
So does that help? So in conclusion, I'll give you one more exercise. It's not exercise, but explanation over here. Imagine this, guys. If I have an electric field piercing through my face, like straight on, okay, onto my, look at the screen right now, and then electric field just coming, piercing through my face right now. What is going to be my net incoming flux through my front part of my face? Of course, you're not going to find area vector of my face. That's going to be crazy, right? Because area vector of my face will point outward in all direction. Does that make sense? Okay. If I have hairs all over my head, that will be the direction of my area vector. But then the only way that the easiest way to think about it is like you shine the light onto my face and you just calculate the area of my shadow on the screen behind me. Does that make sense? Okay, so it's just like you flatten my face down into like two-dimensional piece of screen, and then you paint my face black. Does that make sense? Or it's just like you seeing my face on the screen right now on Zoom, and then you just paint me black. That's it. So that will be the surface area that electric field is going to fall perpendicularly on. That's it. Okay. So in general, if you speak in terms of the vector calculus, the way that this thing is going on, the dots products and the casting of the shadow onto something that is perpendicular on the surface that is perpendicular to the beam of light, something like this. You can think of it, this is like a projection. Okay, so you can think of this one as like a projection. It's like you have a projector shining the light onto some, object, and you look at the area of the shadow. So it's just like you do a projection of a surface onto a two-dimensional screen. So that's why in the vector calculus, this dots product there is another name that you call it a projection operator, because this is an operation that you will be able to find the area vector, the area of the shadow that is perpendicular to the beam of light direction or something like that. So it's just like, it's a real projection. If you want to project light onto some object and you want to figure out the area of the shadow behind this object, you can do this object, the projection operator. So that's what it is. So that has some benefits over here. So if you now, I hope by all of my explanation, and then if you come back here and then do look at this figure again, I hope you kind of understand it now. Look at the slanted surface here. Okay, and if you want to do the projection of that slanted surface onto a screen behind this slanted surface, and the screen is perpendicular to the beam of light, that blackened area there, that is the projected area, right? It's a projection of this slanted surface onto a screen that is perpendicular to the light. Okay?
Okay.
All right, so I hope this sort of will add like an intuitive way of thinking of the flux calculations. Everything stems from the idea that we want only the electric field lines that's going through or penetrate the area in just a perpendicular direction. That's why we need this projection of the actual area, because we want just the area that is perpendicular to the E. Okay, so everything just circle back to the first definition right here. We want just the perpendicular area. Okay, so I hope this works. If not, then just think about it a little bit. It might be a little bit better. All right, but so if you kind of like get the way that we calculate flux, and if you kind of get how can we, do flux calculation on either oriented surface, on and on, here comes the highlights. I already promised you that if you understand flux calculation, the Gauss's law is going to be super simple. So here comes Gauss's law.
Okay.
So I am going to explain this law. And this law is as simple as it gets if you understand the origin of this flux. Okay, so let me trace back here. Remember this problem here that we sort of like practice learning about what is going to be the net flux. Is it positive, zero, or negative, on and on, right? So think about this. Let's start from this one. You have a sphere. Surface is closed. Okay, closed. You have a sphere. So we already said we only care about the closed surface. So there's no ambiguity about the direction of the area vector because area vectors only going to point outward. That's good. So that's fine. Area vector, area vector, area vector pointing outward, right? And in this particular problem, we drew the electric field lines to be pointing in the radial direction outward as well. So we already concluded that the net flux on this one is positive because E and dA are parallel to each other. The angle between them is zero. Now here comes the additional question. Where does this electric field lines come from? Well, Ajahn, it must come from a charge because charge generates field. By having the information that the net flux is positive is a clue that leads to the conclusion that inside this sphere, there must be a net positive charge in here. Does that make sense? Because positive charge generating the field outward. And when you have a sphere wrapping around something and it turns out, hey, the calculation say the net flux is positive, you can conclude that inside that surface, which is a sphere right now, must have a net positive charge in there as well. And that is the Gauss's law.
Okay.
Is that easy? Well, of course. The only way that you're going to get something piercing out, those electric field lines going to come pop out from the surface here, there must be source of that field, source of that electric field lines must be inside that closed surface. So that's why positive flux leads to positive net charge in there. That is the Gauss's law. Look at this one. Right, these two examples showcase the case of net zero, the zero net flux, because the electric field that's enter and leaves having the same amount of flux. So you have no net flux. So the net flux is zero. What does it mean? It means inside this closed surfaces, there must be no charge, no charge, no electric charge. Does that make sense? Because you said, well, net flux is zero. So this will give you the conclusion that there must not be anything inside this container or this enclosed volume or this closed surfaces. Because if there's still some charge left in there, there must be an evidence of a net positive flux if the net charge in there is positive. Or you must get a negative flux if the net charge in there is negative. But because the net flux is zero, the net charge must be zero as well. And that's it, guys. As I said, that's how easy it is for Gauss's law.
Okay.
It's done. If you know how to figure out the net electric flux through any closed surface, we put like a circular sign just to ensure that we only care about the closed surface. Then it will link directly to the charge included inside that closed surface. And because we didn't introduce any constants before, so now it's time for us to introduce a constant to make everything work in an SI system. And now we have an epsilon naught shows up right here.
Okay.
But anyway, the core relationship of this one is just flux means charge. That's it. If you have net zero flux, there must be zero charge. If you have net positive flux, there must be net positive charge. If you have net negative flux, it must be net negative charge inside that volume. Okay? That's easy. Okay?
Okay.
Just to test your understanding, guys. be confident here. Look at this one. If I have a positive charge Q at the center, and somehow I imagine that I have three surfaces, S1, S2, and S3. They're all different shapes. S1 could be a sphere, S2 could look like, I don't know, weird shapes, but doesn't matter. I'm asking you which surface has the largest flux piercing through, S1, S2, or S3. Right, it's not that big. The answer is they're all the same. Why? All right, you can think of it in one way. It's just like Ajahn, if you count the number of electric field lines, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, usually you don't do this, but just based on this figure, the 12 lines piercing through these three surfaces, that's it. So these three surfaces experience the same amount of electric field lines. So same amount of flux. But now think in terms of the Gauss's law. S1, S2, and S3 wrapping or enclose the same amount of charge, which is Q. So I can tell you right away, the net flux through these three surfaces must be Q over epsilon naught. And that's it. I'm done.
Okay.
Is that easy? It is that easy. Try again on the right. If I have a figure on the right, I have some weird surface. I don't know what it is, but then inside this closed surface, it does not wrap any charge in there. The charge somehow stay outside. I can tell you right away, flux on this surface will be 0 because there's no flux in it. That is Gauss's law, guys. And we are done.
Okay.
Is that a go? All right. It's very good for holidays lecture over here. It's just like, okay, this is going to be like a breeze today. Right. And that's how simple it is to conclude about Gauss's law. So let's test a very quick, understanding of this one. So a figure shows in cross section. So it means you have to think in three-dimensional space over here. So you have two Gaussian spheres. So when you see this adjective in the front of some shape like Gaussian this, Gaussian that, it just means you are building or visualizing a surface that you are going to be used in, that it's going to be used in the Gauss's law determination and all this stuff, right? So that's why they call it a Gaussian sphere. So the imaginary surface that you use to wrap the charge around, that is your Gaussian surface. All right, cool. So this S1, S2, S3, and the surface that we just drew over here, that can be named Gaussian surface. It's imaginary, guys. There's no real, it's no real surface or anything. It's just, it's just a theory, right? It's a law saying that you can wrap around the charge in any shape, in any form you like. This has to be followed at all times. That's the law. All right, so you have two Gaussian spheres. So you think of that, the orange sphere and the green spheres to be wrapping the charge plus Q at the center. Plus, you have two Gaussian cubes. So that box over there represent like a three-dimensional cube wrapping the charge positive Q in there. So rank the net flux through the four Gaussian surfaces. Greatest first. Whoa. Which one will give you the greatest flux? Guys, be confident here. Same in all four surfaces, right? Why? Because these four surfaces wrapping the same amount of charge plus Q. So that's it. Not only that, I can even tell you the net electric flux throughout these four surfaces must be plus Q over epsilon naught. And I'm done.
Okay.
It's too easy. All right. And this one is exactly what's supposed to be, because imagine that if you draw the electric field lines coming out of this, the electric field lines has to go through these four surfaces with the same amount of lines, same amount of flux. So the net flux through these flow surfaces must be the same. But by Gauss's law, I can even tell you quantitatively that the total amount of flux is going to be Q over, wrong, sorry. Q over epsilon naught. Perfect. I know quantitative value for this flux as well. Nice. Okay. All right, guys. So this slide over here is showcasing how to apply Gauss's law. And I mean, from the experience, by reading through this doesn't really help because you don't know what you want to do with this Gauss's law just yet. So even though I keep talking about this slide, explaining this and that, you're not going to see anything. So what I'm going to show you is learning by example. Once you look at some example, that will be the easiest way to learn. And then you start to observe the characteristic of this Gauss's law, and then you will know how to apply this one later. So instead of showing you this, I am going to walk you through this step by step and do this thing together. Okay, this is gonna be fun. All right, so I'm just gonna start from scratch, and let's see if you guys agree with me. So think about this, guys. So if you have a positive charge plus Q, okay, and now somehow you say about John, I want to figure out the electric field at some point P, and point P is at the distance r away from this charge. You start to think about John, we know how to do this already because we already had the Coulomb's law. Coulomb's law will give you the electric field at point P to be K, the charge generating the field Q divided by the distance square. So that's it, you're done. You can apply Coulomb's law, right? But now I am going to use Gauss's law. And let's see what happens. So how can we apply Gauss's law here? First thing first, the charge is just a point charge. So you think of a point in a blank space. When you are in a blank space, like super dark, you don't see anything. There is not going to be any up, down, left, right, front, back, north, south, east, west, none. You cannot even tell. They all look the same to you. No matter which direction you look at, they all look the same. What we have over here is called spherical symmetry. Does that make sense? It's spherical because you can look around you in all directions. They all look the same. And that spherical symmetry suggests that you should draw a Gaussian surface to be in the shape of a sphere. Cool? So that means what I'm trying to say is I'm using symmetry to determine what shape of the Gaussian surface should I pick. And because I have a spherical symmetry, I should pick a sphere. So I hope I draw. Okay, is it good? I hope it's good. It's a little smaller. There you go. Give me a little bit of time here. Okay, here we go. Come on. Make it nice. Here we go. Pretty good. All right. So that's it. So I'm picked sphere to be wrapped around this charge plus Q, and it's in the shape of a sphere, right? So the good thing about this one is we already know the dA. Every time that you slice a tiny piece of this, the area vectors always point perpendicular to it, perpendicular to it, perpendicular to it, perpendicular to it. Everywhere, it's going to point radially outward. All right. Now, what about electric field? Because of this spherical symmetry, you know that this positive charge is going to generate electric field somehow. But because of this spherical symmetry, electric field should have a uniform magnitude in all directions because you don't have any preferred direction. There's no up, there's no down, there's no front, back, north, south. There's no particular direction that you should have electric field to be stronger than the other, right? There's no sense. There should be, then there's no bias pretty much. So that's why the argument will be the electric field supposed to point in the radial direction equally in all directions as well. See? So I don't know much about anything. I only know about the symmetry of the problem. I still don't know the magnitude of the electric field. I don't know the Coulomb's law. I'm not doing anything. I just imagine a Gaussian surface to be in the form of a sphere, and I just argue that the electric field is supposed to point out in all directions equally. All right, now here comes the Gauss's law, guys. So what I'm going to do right now is I'm saying that, hey, I'm just going to calculate the total flux on this Gaussian sphere or Gaussian surface here. And it's going to be integral of E dot with the dA across this sphere. Cool? But when you look at this one, E and dA are parallel to each other, so the angle is 0. So it's going to be E dA cosine 0. But then we already said electric field is supposed to have the same magnitude in all directions. So it doesn't matter which point you're looking at on the sphere. Electric field magnitude is supposed to be exactly the same. And what is the integral of the dA? Oh, Ajahn, integral dA is just the dA, 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 dA. You just sum all those tiny pieces of area across this sphere. So that means this integral will just give you the surface area of this sphere, which is 4 pi r square. That's it. That is the net flux through this sphere. Cool?
Okay.
And Gauss is safe. If you figure this out, this must be equal to the charge inside this Gaussian surface divided by epsilon naught. How much do you put there? Well, Ajahn, you only have positive Q inside this sphere. So you just put positive Q in there. And that's it. That's how easy it is to apply Gauss's law. But when you look at this one, Ajahn, E is on the left. That's kind of neat. If I should start like move the 4 pi r squared to the right, I should be able to conclude that electric field E is 1 over 4 pi. Now I combine this with the epsilon naught on the right, keep the Q there, R squared is there. Does it look familiar? Yeah.
Okay. Okay.
This is a wow, wow, wow moments, guys. This is like a jaw-dropping moment for you guys here. You get back the Coulomb's law. No? No. Okay, fine. But anyway, that's what it is. And the constant that we were introduced in terms of the Coulomb's constants now is in another form, as I mentioned earlier. Like, hey, it could be two ways of writing these constants. It's either in the Coulomb's constant K, or eventually it's going to link to the other constants, which is we use an epsilon naught in the Gauss's law. But now from this, we can say K is 1 over 4 pi epsilon naught. And the epsilon naught actually has the name. So the epsilon naught over here, this is permittivity of free space. When you say free space, you can think of it like a vacuum. Think of it that way. It's like nothing there. It's a vacuum. Okay. So that's why there's a naught sign right there. Just the naught is just to saying that, hey, it's just blank space. There's nothing there. Okay. So this is it. So Gauss's law eventually lead you to the same result as a Coulomb's law. So actually these two laws are equivalent. They're saying about the same thing. And they say about the same thing about the relationship between the charge that is generating the field. And that concludes this slide right here, guys.
Okay.
Cool. All right. And I think I'm going to pause right here. All right. Take a quick break. And after this, I'm going to show you a couple more exercises that allow you to see how to apply the Gauss's law. And once we're done with that, and if you come back and take a look at this slide, it will make more sense. By learning by doing, it's much better than just going through some theoretical suggestions and then you don't know anything at all. Eventually you have to learn to do the exercise anyway. All right, guys, so let's take 10 minutes break right here and then we'll see each other 10:55. Sounds good. All right, okay, so take 10, guys. Let's get back to Gauss's law a little bit more. And right, today's lecture is not going to be that long, so I think sticking around a little bit, I'll have 4 more examples to show you, and I think we're done. Okay, sounds cool. All right, so let's dive into it. And at the end, I'm going to summarize this page one more time, and I hope it makes more sense by looking at examples first. Okay, all right, a little bit more, guys, but it's gonna be like kind of fun. So let's take a look at this. I have first example. Look at this one. I'm gonna extend from just a point charge. Let's do something more realistic. Let's say if instead of having just a point charge, you have a ball. It's a solid piece of object that has the charge distributed across the ball. So it's a solid sphere. Okay, and the charge are sort of like scattered around uniformly across this ball over here. So to do this the easiest way, even though you know that maybe it's given that, hey, the net amount of charge in this ball is capital Q, but the way that we can define this amount of charge in this like three-dimensional object is by using density. You guys remember density?
Okay.
Back in the day of the like a charge on a rod, when we did the calculation in the electric field, you were looking at like a lambda, which is the charge per length. Yeah. So all right. So that's not bad, because every time that we have this density and you want to get back to the charge, you just multiply by the length, you get back the charge. So we can do the same thing over here. But now because it's three-dimensional object, we're gonna define rho. All right. It's now is going to be charge per volume. So this is quite intuitive because it's very close to the concept of the mass density. Mass density is charge, is the mass per volume. But now we want charge density, so it's a charge per volume. Okay. So by having this, it means every time that you want to figure out the amount of charge, all you need to do is just taking the rho multiplied by the volume. You get the charge that you want. That's easy. Okay, so that means instead of define the total amount of charge alone, you can define like a rho on this one. So it say, okay, John, the density of the charge inside this solid piece of sphere here is rho. So the Q and the rho are related through simply by taking the rho and multiply by the volume of this sphere. It's a 4/3 pi capital R cube. And the capital R is supposed to be A then. Sorry, my bad. So A is R. All right, that's okay. So that's what it is. All right, charge can be calculated from the density easily by just multiply by the volume. Now, let's start from the electric field outside the sphere. Well, John, let's say if I'm standing at some distance, okay, let me point right here, P, and I want to find out what is the electric field at point P. So what is electric field at point P? You want to know. Well, John, why don't we use Coulomb's law? We already knew how to do this. Well, okay, you want to try that? Yeah. So if you want to do the Coulomb's law, you have to slice this ball into a tiny piece dq first, right? Sort of like doing calculus here. You slice, pick a tiny piece of charge, and you measure the distance from this point to point P. You can call it R. And then you say, hey, electric field is just K dq over R squared. But then the problem is you have to put, this calculation to the next piece of dq, next piece of the dq, next piece of the dq, next piece of the dq. So it's mean you just have to do this, to do that, to do this, to do this, to do that, everywhere on the sphere. And you can imagine that whatever k dq over r squared that you have to do it like a triple integral. Makes sense? Why? Because the ball is three-dimensional object, and you want to do the k dq over r squared throughout this three-dimensional object. So you cannot avoid you doing three-dimensional integral. And who will want to do that? No, right? No way. So what we want, we will not do that at all. Even though you can, and I think it can be done actually. Um, I think maybe the textbook will do that for you. I guess I don't know. Was I think I delete too much. All right, so I only want to delete this. Okay, give me a second here. Yeah, here we go. All right, that's good. All right, so we don't want to do that. So what we want is to figure out the way to find out electric field at point P using Gauss's law. Once again, because this solid ball is still a three-dimensional object that has a spherical symmetry. I mean, the shape already suggested that, hey, Ajahn, it's in the form of a sphere, so it should still have the spherical symmetry. All right. So that means if you have this ball in a blank space, this ball cannot tell is what's up, what's down, what's north, south, east, west. There's no directional. So that means it's the same in all direction. So that leads to the that leads to the a conclusion that you should pick a Gaussian sphere to be in the form of a sphere as well. Sorry, you should pick a Gaussian surface in the shape of a sphere as well. Sorry. All right, so that's what it is. So I'm going to pick a sphere to wrap around this ball, and that is your Gaussian surface. This is your Gaussian surface. Here we go. All right. And you can name it a Gaussian sphere. That's the surface in the shape of a sphere. So what you want to calculate is the net flux on this sphere. But John, no problem. We did that before. It's a form of the sphere. So the dA will point radially outward everywhere on this sphere, just like previous example. And by symmetry, electric field lines supposed to point out in the radial direction equally. The reason is because there shouldn't have any particular direction that electric field is stronger, because it doesn't know what's up, what's down, what's left, what's right. So that's what it is. Everything look exactly the same. So I'm going to calculate net flux on this sphere. So let's go for it. Net flux is integral E dA, and we're going to do a full integral across this surface. So I put a circular sign on it. And the way to do that, all right, let me do a detour over here. It's going to be equal to integral E dA cosine 0, because E and dA are parallel to each other. And because E is supposed to be exactly the same in all directions, so there must be a constant magnitude. I can pull it out from the integral. Cool. Very nice.
Okay.
And then because, I don't even have to put cosine 0 anymore, because cosine 0 is 1. And the dA over here is just the dA, right? It's just the sum of all those dA across this sphere. So that is going to give you 4 pi r squared. And that's it. It leads you back to this, E 4 pi r squared. That's it. That's the net flux on this sphere. And then you equate to what? You equate to the right-hand side, you put the charge included inside this sphere divided by epsilon naught. How much charge is inside this Gaussian surface? Well, Ajahn, the whole ball is in here. So that's mean the total amount of charge is included here. So that's why you plug in the Q in here. That's it. You're done.
Okay.
And you can see that Q is waiting for you right there. You just move 4 pi r squared to the right-hand side, check. And that's it. That is the electric field.
Okay.
That's see, no more triple integral. There's no Coulomb's law to integrate or anything. You can re-express Q in terms of rho if you like. So you can say you plug in this expression here into the expression, depends on what kind of information you have. You have the Q or you have the rho. But that's it. That's the application of the Gauss's law. Isn't that cool? All right. If you feel this is kind of cool, move on to the second example here. What if I want to figure out the electric field inside the ball? Whoa. Okay, so outside is fine. What about inside? Well, Ajahn, well, of course, we're not going to try to do any Coulomb's law anymore, of course. So we're going to still using the same trick. No matter it's outside or inside the ball, it still retain the spherical symmetry, right? Okay.
Okay.
So that means you still built a Gaussian surface in the shape of a sphere. Same thing. So now you pick a new location there. So let me call this like point P. Again, this is a new P. So you want to figure out the electric field at point P, but now P is within the ball. So that means the distance R is less than the radius of the ball. So you just build the Gaussian surface again, but now just make the surface to include point P on it. And then by the same argument, due to the spherical symmetry, electric field still supposed to be pointing radially outward. What else can it point to? Right? Because of the symmetry, plus all the surface dA point in the radial direction as before. dA, dA, dA. So again, it looks exactly the same as the previous example, except the Gaussian surface is smaller. Yes, that's what it is.
Okay.
So let's do it. Calculate the net flux on this one is the integral E dot dA across this Gaussian surface. Okay. And once again, you say, okay, it's just E dA cosine 0. E is supposed to have the same magnitude in all direction. They shouldn't have any particular direction that the electric field is stronger than the other. So that's good. And then the integral of the dA is just the surface area of this Gaussian sphere, 4 pi r squared. This is what you get. And now you equate that to the charge included divided by epsilon naught, right? Now here comes the question. How much charge you supposed to put into that box, the Q included? Now the answer is you're not going to take the whole big chunk capital Q because that Q is the total amount of charge on the whole ball. But what you have right now is just this much. So you can imagine like this is like an ice cream scoop. The capital Q is like a big scoop there. But what you want right now is a smaller scoop, smaller one. So how much is that? And that's the utility for that rho. So now if you know that the rho is given, so Q included over here is just going to be the rho, that's the charge density, and then you just multiply by the volume, 4 third pi small r cube. You guys with me here?
Okay.
Yeah, so that's it. So if you know the volume, you multiply by the density, you get the amount of charge. But because now your radius is small r, and that is not going to give you the total amount of Q. So that's it, guys. You just take this. Q included, plug it in here. Bam. And that's it. This is what you have. Rho 4 third pi r cube, 4 third pi r cube rho. And all you have left is just take the 4 pi r square, move to the right hand side, 4 pi r square with the epsilon naught. And that's it. You are done. That is your electric fields inside the ball.
Okay.
See, no more no triple integral for you to think about. You just purely use the symmetry of the distribution of charge, and you come up with the Gaussian surface in the form of a sphere. Why sphere? It reflects the spherical symmetry of the charge distribution here. And this you're done. And actually, I can cancel a little bit more if you like, bam, bam, and write this a little bit cleaner. Put it in form of like R rho over 3 epsilon naught. What you can see over here is the electric field inside is proportional to R. Cool. So what does it mean? It means if you are standing at the center of the ball, you're supposed to get the zero field, which makes perfect sense because if you're standing right at the center, the electric field will all cancel each other out. So you shouldn't have any net positive or negative electric field whatsoever. So at the center of the ball, the electric field is zero. And when you walk away from the center, electric field getting stronger, stronger, and stronger. So it means if I want to plot a curve, the distance r with the strength of the electric field, and this is the radius of the ball. The A is the capital R there. So it means start from 0, electric field is going to go linearly. That is proportional to R. But once you reach the surface of the ball, now electric field is going to be proportional to 1 over R square. It's dying down just like Coulomb's law. So that's it. Bam, right there. E is inversely proportional to R square. And you are
Okay.
Okay, so this is a very good two starting examples to showcase how to apply Gauss's law. Not only that, if you do the analogy between the electric fields and the gravitational fields, you can use this explanation to explain if you think of the Earth to be like a big solid piece of mass uniformly distributed, you can tell that when you're standing at the center of the Earth, you have zero gravity. And if you walk away from the center of the Earth, then the gravity is increasing, increasing, increasing until you reach the surface of the Earth. And once you lift yourself away from the surface of the Earth, the gravity is dying down 1 over r squared as well. Isn't that cool? All right. But we
Okay.
didn't have any Gauss's law. I mean, we didn't do the Gauss's law in gravity, but at least by learning this from electricity, it's allow you to understand what will be the change of the gravity, the G, in the gravitational field as well. Cool. All right. But the bad thing is, of course, Earth is not like a piece of solid mass uniformly distributed. So, all right, it's not realistic calculation anyway. So yeah, it's lava, right? It's the hot melted stuff in at the center of the core of the earth and all this stuff. So all right, so but at least this is a good theory to learn. All right, so I hope you understand this application, and if you start go back and then try to read this slide, it's getting making more sense over here, because here the value of the electric field here, we use the argument of the symmetry to select the Gaussian surface. So the Gaussian surface, we try to be clever, pick the shape of the Gaussian surface to be something that make our life easy. For example, it's a constant over the surface. See, that's what you saw before. The reason that we pick the Gaussian surface to be in the shape of a sphere, because the electric field on this sphere having the same magnitude. So if you decided to pick like a box, like a cube, then you're gonna have a hard time figuring out the electric field, because you don't know the variation of the electric field on the surface of a cube, right? But if you have a sphere which reflects the spherical symmetry of the charge, then you can argue easily like, hey, electric field is supposed to have the same strength in all direction, because they don't have any preferred direction. Cool. All right, that's it is. All right, so do two more. All right, and now I'm just gonna put some variation to the problem. Instead of having a solid ball, now I have a spherical shell. So shell, you can think of it like a ping pong ball. Think of it that way. It's a shell. Okay, so there's no something inside. It's just a shell, thin shell. So the question is, if you have a thin spherical shell, so let me draw that one, okay, and the charge just distribute across the surface of this shell, and they said that the total amount of charge on this one is Q, that is fine. What is the electric field outside and inside the shell? Same question, okay? So, well, Ajahn, if you're standing at some point away from it, that the center and the distance from the center to that point P is R by spherical symmetry of the shell. This suggests that you should pick your Gaussian surface to be in the form of sphere. Again, oh, get sick of it already, Dan. Again, oh, yeah. So your Gaussian sphere, I'm sorry, the Gaussian surface is going to be in the form of a sphere again. Okay, let me do it. There we go. Very nice. Yeah. Whoa. Okay. So one more time. It's the spherical symmetry. So the Gaussian surface is in the shape of a sphere. Then you just do the same thing as you did before. What is the net flux on this surface? The surface is the dA. dA is pointing out in all direction equally, perpendicular to the actual surface. Due to the spherical symmetry, the electric field is supposed to point out in the radial direction as well, and equal in magnitude. So E and D, oh, sorry, E and D, oh, I shouldn't put DA there, sorry, just E. Here you go. So And now you just calculate flux on this surface over here. So it's going to be integral E dot dA across this surface. And because E and dA are parallel to each other, so it's E dA cosine 0. And because E is supposed to have the same magnitude, and the integral of the dA, you just get back the surface of this Gaussian sphere. That's it. You're done. You've seen this like this is the fourth time seeing this already, right? Well, okay, I got it. This is how you calculate the flux. Once you're done with this, you equate this to the right side. So all you need to plug in here is the total amount of charge inside your Gaussian surface, and then you're going to divide it by epsilon naught. Here comes the question. How much charge should you put in there? Hmm. Done. This sphere cover the whole charge Q. So don't think too much, guys. Just put Q in there. That's it. You're done. And that's it. You can just move things around. E is waiting for you there. So that's it. You can conclude that E outside is just 1 over 4 pi epsilon naught capital Q over R squared. And that's it. You are done.
Okay.
It looks like Coulomb's law, guys. KQ over R squared. So you start to see the similarity of the whole results that we have been doing in the past 4 examples. This one, okay, this one here. Yeah. This looks like KQ over R squared. The dots, there's no doubt, this is definitely from Coulomb's law, KQ over R squared. So in conclusion, it doesn't really matter. You have a point charge Q or a solid ball Q or a spherical shell Q, as long as you are far away from it. That means you look at it and look like a sphere. The electric field that you experience will be in the form of Coulomb's law, KQ over R squared, no matter what. Isn't that cool? All right, so that's kind of nice. Nice in the sense that you don't have to worry too much about the actual shape of your charge as long as it has a spherical symmetry. It could be a point charge, it could be like a bead, like a mini ball, like a boba ball, mook or whatever, or it could be like a ping pong ball. As long as you are away from it, the electric field strength that you experience from the ball will be all the same, KQ over R squared. And that can be verified or proven using Gauss's law here. Right? It will be tough to use other law to prove it because it's going to be like a three-dimensional, calculus, as I already mentioned. All right, nice. Okay, let's do the last example, guys. What about electric field inside this shell? บอกอาจารย์ you just pick another position right there. So let me now, I'm standing at point, let me call this like point M, which is now inside this spherical shell. By symmetry, we are still working under spherical symmetry anyway. So that means the Gaussian surface that I should pick must be in the form of a sphere. So let's look at the green here. There you go. All right. So you do the flux calculation on this sphere. Okay, let me put the green here. So I want to calculate flux on the green one right there. So that is going to be E dot dA on this green surface. But no matter what it is, your dA is still pointing radially outward dA, radially outward dA, no big deal. And due to the symmetry, the electric field is still supposed to point in the radial outward direction as well. It shouldn't have any particular direction that has a stronger electric field than the other. Same argument. So what you have is they're gonna look the same. Get sick of this already. This is the fifth time doing this. It's the EDA cosine 0. E is supposed to have the same magnitude everywhere. And the integral of the dA will give you just the surface area of the Gaussian surface, 4 pi r squared. And now r is just it's just r is just smaller than the radius of the shell. That's all. And then all you have to do is just, well, John, you equate this to the charge inside Whatever that is, you divide it by epsilon naught, and then you're almost done. Here comes the question. How much charge should you put in the right-hand side of this Gauss's law? Well, Ajahn, all the charge here are just, okay, let me highlight it. It's just on this shell. It's a thin shell, right? You have a positive charge Q lying around on this thin shell. But your Gaussian sphere now is smaller than the shell. So if you look inside this Gaussian surface, isn't there, is there any charge in here? No, there's no charge. So you put zero in there. Does that make sense?
Okay.
There's no charge. It doesn't include any charge. So that's it. So that leads you to the conclusion that electric field inside must be zero. And you are done.
Okay.
And that makes quite a good sense of this one because this has a little bit of connections to the reason why when once like when you are in the elevator or when you put like in the movie that they put like a cell phone in a microwave, it won't get any signal. That is because the the container of either the elevator or the microwave is made out of metal. And usually metal will have like, think of it like if you have like a leftover charge, you are being wrapped around with the charge container. So electric field inside is zero. Does that make sense? It might
Okay.
not, I mean, this is not a good example per se because in reality, when we talk about the microwave or we talk about the cell phone signal, it's an electromagnetic wave. It's not like an electrostatic, but it has some connections in calculating what is the behavior of the electric field after hitting like a metal surface. All right. And it's sort of like diminishing the electric field afterward. So another scenario that might be interesting is just like if you get a lightning strike and you're staying inside a car, as long as your body does not touch the body of the car, you should be safe. Because once you get the lightning strike, the car, the body of the car, which is made out of metal, is get charged, right? You're supposed to be safe in there because you are inside a cage. Think of it like a cage, and it's a charged cage. So electric field inside is supposed to be zero. So, well, but in reality, it's gonna be a lot more troublesome because lightning will ionize the air around you, and then part of the air could conduct electricity on. So you might not be perfectly safe there, but at least, I mean, in theory, saying that if you are inside a charged container, the electric field inside is supposed to be zero. That's what it is. Okay. All right. So that's the 5 examples starting from a point charge. That's verify the Coulomb's law one more time. A solid ball, you know how to calculate electric field outside and inside. You have a spherical shell, you know how to calculate electric field outside and inside. As you can see, just apply Gauss's law in the same manner. You are able to calculate electric fields in all cases here. Okay, and now if you go back and read this process over here, see, you try to make the algebra of the flux calculation as simple as possible. And as you can see there, we try to pick the surface that electric field and the dA are parallel to each other. So that's kind of nice. And next time we will have other chance to try to do, right, pick a surface that maybe make E and dA perpendicular to each other. So everything goes to zero, on and on. All right. So that's the application of the Gauss's law is we try to utilize the symmetry of the problems. That's all we can argue about. We don't have any Coulomb's law to use. We only use the symmetry arguments to set up Gaussian surface and do the flux calculation and pull in the Gauss's law, and bam, that's how we calculate electric fields. Not bad, I hope. All right, guys. So I think I'm gonna stop right here. I think it's already too much, but as I said, I hope this is like a highlight of the course here because this law is kind of new and it's kind of like different approach in relative to everything that you have learned before back in the Newtonian physics, back in the thermodynamics, or even like electricity and magnetism back in the high school days. All right. So I hope this is kind of new and it's include a little bit of vector calculus right here. But as I said, a little bit because you saw it. You do it 5 times, bam, it's repetitive. All right, guys. Thank you so much
Okay.
for sticking around. I'll see you on Saturday. Okay. And just show up a little bit early, guys. Just like 9 o'clock in the morning, if you can make it. All right, guys. Thank you so much. I'll see you on Saturday. Bye bye. Take care. All right, stay safe. Thank you, Cap.